This is section 2.1, Relations and Functions. We have a few objectives today. I can determine the domain and range of a graph, graph a relation, and evaluate a function. A function is a relation in which each element in the domain is paired with an element in the range. What is a one-to-one function? It means that each element of the domain pairs to exactly one unique element in the range. And remember, when we're talking about domain, we're talking about x values. When we're talking about range, we're talking about y values. What is an onto function? Each element of the range corresponds to an element of the domain. And can a function be both one-to-one and onto? Yes. In our first set of questions, it says to state the domain and range of each relation, and then determine whether each relation is a function. If it is a function, we're going to tell if it's one-to-one, onto, both, or neither. So, first of all, you'll have to fill this in, because I noticed that when it went over to Canvas, it did not copy the examples over, so you'll have to fill those in. So this is just a set of points. And first we want to determine if it's a function. And the way that we're going to do that, we're going to look at the domain and make sure each piece of the domain, so each x value, has a y value. And in this case, -6 has a -1, -5 has a -9, -3 has a -7, -1 has a 7, and 6 has a -9. So this one is going to be a function. So I'm going to write yes. Each element of the domain is paired with one element of the range. Alright, now we want to decide if it's one-to-one. And what we're going to do for that, we're going to see if the range is unique. So pretty much what we're looking for is if the range repeats, if the y values repeat, do they go to different x values? And in this case, we see that we have a -9 here, and we also have a -9 down here. So those are our only y values that repeat. Now, if our x value on both of these was the same, then we would say that it was one-to-one. But in this case, -5 maps to -9, and then 6 also maps to -9. So for one-to-one, we're going to say no, because there's not a unique range. Now let's talk about onto. We want to make sure that each range has a domain. So if we go and look at our y values, -9 has the x value of 6, 7 has the x value of -1, -7 has the x value of -3, -9 has the x value of -5, and -1 has the x value of -6. So we're going to say, yes, this one is onto. And our reason is because each range has a domain. One other thing that they wanted us to find was the domain and range. So domain is always going to talk about the x values, and range is always going to talk about the y values. So we're going to go ahead and write those down. So our domain, our x values, we have -6, comma, -5, comma, -3, comma, -1, comma, and 6. And we always want to make these be in brackets. And then for our range, we're looking at the y values. So we're going to have -1, comma, -9, comma, -7, comma, 7, and then we do have another 9, or we do have another -9, but since we already wrote our -9 once, we don't need to write that again. So I'll go ahead and close my brackets. Let's go ahead and look at example B. Now on your paper for your notes, it looks like this. It should actually be a table, so you'll have to go ahead and fix that. And we're going to talk about, is it a function, is it one-to-one, is it onto, and we're going to state the domain and the range. So thinking about, is it a function, we want to make sure that each x value only goes to one y value. And here we have 2 going to -2, and we also have 2 going to +2. So we know that it's not going to be a function because of that. We also see that happen with -1. -1 is paired with -1, and -1 is paired with +1. So when we're saying if it's a function, we're going to say no, because each value of the domain isn't paired with exactly one element of the range. And then, since we went ahead and said that this is not a function, we don't need to do one-to-one, and we also don't need to worry about onto. I do want us to talk about the domain and range. So for the domain, remember we're talking about the x values. We're going to have 2, -1, -2, and then our other 2 x values are -1 and 2, and we've already written those, so we don't have to repeat. We're going to go ahead and close that up. With the range, we're talking about the y values, so we have -2, -1, 0, 1, and 2. And folks, when you're writing the domain and range, you don't need to write those in any particular order. You can just write them down as they give them to you. So here I just wrote them directly in order. You don't need to worry about writing it from decreasing order to increasing. That's okay, it doesn't matter. Looking at example C, we have a graph, and that actually did print out for you guys. So when we're determining if this is a function, remember we want to make sure that our x's don't go to more than one y value. So you guys may have seen something called the vertical line test, and we can go ahead and look at that here. We want to make sure that any line that we draw vertically, so up and down, does not hit more than one point. So for this C value, it doesn't hit any other dot. For B, dot B, it doesn't hit more than one point. For dot E, it also hits this D. So this E and this D are on the same line, so we know that this is not a function. So no, not a function, because each value of the domain is not paired with exactly one value of the range. So remember, we don't need to worry about saying if it's onto or one-to-one, since it's not a function. However, I do want to look at what the domain and range are of this guy. So if we go ahead and talk about the domain and range, domain, we're wanting to talk about all of the possible x values. So if we look at the x value of C, we know that the x value is -6. So -6 is in the domain. Then looking at our point B, we know that it goes with the x value of -3. Then looking at E and D, we know that the x value is going to be 0. Looking at F, we see that the x value is 4. Looking at, let's see, A, the x value is 5. And looking at the G value, we see that the x value is going to be about 6.5. And that's all of our points. And then we need to talk about the range. So we want to talk about all of the y values. We're going to do the same type of thing. We just are writing the y values down. So for C, we see that the value is -4. For B, we see that the y value is 1. For E, we see that the y value is 0. For D, we see that the y value is -3. For F, the y value is -5. For G, the value is also going to be 0, but since we already wrote the 0, we don't need to write that again. And then for A, our y value is +3. A relation in which the domain is a set of individual points, like the example we just looked at, is said to be a discrete relation. Notice that its graph consists of points that are not connected. When the domain of a relation has an infinite number of elements and the relation can be graphed with a line or smooth curve, the relation is a continuous relation. With both discrete and continuous functions, you can use the vertical line test to determine whether the relation is a function. And this is what I was just talking about. So we want to make sure that anywhere we draw a vertical line on these graphs, we're going to see if it hits more than one spot. On this one, you can't draw a vertical line in any area and hit more than one point. So we know that the first graph is going to be a function. However, on the second graph, we can see that this vertical line hits here and here, so we know that the example 2 is not going to be a function. On the real-world examples, let's take a look at graph A. The graph shows the relationship between the number of cartons of eggs bought versus the total cost. Is the relation discrete or continuous? So, since this is made up of lots and lots of little dots, we can't draw a smooth curve. So we can't just put our pencil down and draw a line without picking it up. We have to pick it up to move from dot to dot. So this one is going to be discrete because of that. And then does the graph represent a function? Well, we can do the vertical line test. We know from here we only hit 1 point. Here we also only hit 1 point, and here we'll only hit 1 point, which my lines aren't perfectly straight or anything, but we're not going to ever hit more than one value. So this one is going to be a function. Let's take a look at real-world example B. It says the number of employees a company had in each year from 2004 to 2009 was 25, 28, 34, 31, 27, and 29. Graph this information and determine whether the relation is discrete or continuous. And does the graph represent a function? So first, I went ahead and labeled these, some values on the x-axis, some values on the y-axis. And on the x-axis, I'm counting by ones, 2000, but starting with 2000. So 2001, 2002, 2003, 2004, on up. On the y-axis, I'm counting by fives, 5, 10, 15, 20, so on and so forth. So let's go ahead and graph these. In 2004, that's the first year, it was at 25. So I'm going to go on up and make my point. Which is right around here. And then in 2005 would be the next year. It's on up to 28. It would be about right here. Oop. Mine won't be exact since I'm doing it with this app, but yours can be very precise. And then in 2006, we're looking at 34. Which will be about right here. Oop. And then, let's see, 2007 would be next, and we're looking at 31. And then for 2008, we're looking at 27. be about right there. And then for 2009, our last one, we're looking at 29. Okay, now yours will be more precise than mine is, but this is about what it's going to look like. So when we're asking ourselves, is this discrete? Since we were just plotting points, this is going to be discrete. And then when we ask ourselves, is this a function? Again, using that vertical line test, we're never going to hit more than 1 point. So, yes, it is a function. Now let's look at graphing relations. In example A, it should say to graph y equals 1/2 x minus 3. So, what I'm going to have you do is create a t-chart. And very standard values for us to use is -2, -1, 0, 1, and 2. That's going to give us a good idea of what the graph is going to look like. So to get those y values, remember we're just plugging them in, we're plugging our x into the equation. So for example, on number 1, or on the first one, we'd have 1/2 times -2 minus 3. So -2 times 1/2 is -1, -1 minus 3 is -4. So you're going to do that to get each y value, and you'd end up with -3.5 for -1, -3 for 0, -2.5 for 1, and -2 for 2. So if we go to graph those, we're going to go to -2, -4, we'll go to -1, -3.5, we'll go to 0, -3, we'll go to 1, -2.5, we'll go to 2, -2. And mine aren't exact, but yours will look better than mine. And what this is going to do, this is going to create a straight line, which your line will also look better than mine does. But now we need to determine whether it's a function, one-to-one, onto, both, or neither. And in this case, our x's only go to 1y. It does pass the vertical line test, so this one is going to be a function, and it's going to be one-to-one and onto. And then we have to tell if it's discrete or continuous. Since this is a line, so yes, we did come up with points, but anytime you have a function, so anytime you have y equals or you have f of x equals, it's going to create a line. Okay, so these aren't just dots, these are creating a line. So this one is actually going to be continuous. They also say that they want the domain and range. So if we're talking about the domain, we know that it's talking about x values, but since this isn't points, so we're not just using these, we want to see, does it go to the right forever and does it go to the left forever, and are there any gaps? In this case, since he's going this way forever and ever and ever, it'll cover every x value this way, and since he's going this way forever, it'll cover every x value that way. And we're not going to have any gaps. So for domain, we have all real numbers, and we can just write our fancy R. And then for our range, it's also going to go up forever and be going down forever with no gaps. So in this case, our range is also going to be all real numbers. Looking at example B, it should say graph y equals x squared plus 1. We're going to do the same thing here. We're going to make a table of values, or a t-chart. So remember, we're plugging in, so we have -2 squared plus 1. And if we have this -2 squared, we're going to end up with 4 plus 1, which is 5. If we do -1 squared, we're going to get 1 plus 1, which is 2. 0 will give us 1. 1 will give us 2. And 2 will give us 5. So if we graph this, we'll end up at 0, 1. and negative 1 up to 2, and negative 2 up to 5, one up to 2, and 2 up to 5. And if we connect all of these, this one is going to create a U. And so we want to look at this, we want to determine the domain, and in this case it is going to go towards the right and towards the left forever, so domain is all real numbers. Our range, however, is going to be y is greater than or equal to whatever the lowest value of y is, which in this case is 1. So y is going to be greater than or equal to 1 because these arrows are going to go up forever, but we're never going to hit any of these y values down here. And this one is going to be a function, but it's not going to be onto or 1 to 1. And then we can also say that this one is continuous because it's a line. When an equation represents a function, the variable, often x, with values making up the domain, is called the independent variable. The other variable, often y, is called the dependent variable because its values depend on x. Equations that represent functions are often written in function notation. Now you guys have some words that are missing down there, but I'm going to tell you what it says. So a lot of times you all have seen y equals 5x minus 1. Function notation just means we're writing f of x equals 5x minus 1. So really it's the same thing. Now suppose we want to find the value in the range that corresponds to the element negative 6 in the domain of the function. So really what we're going to be doing is substituting in negative 6 for our x, which means we're going to have f of negative 6 equals 5 times negative 6 minus 1. And then all we're going to do is evaluate the right-hand side. I have a lot of students that try to do something with this. This is really just a notation, so we're not going to do anything with the left-hand side. We're just going to evaluate. So we're going to have 5 times negative 6 minus 1, which is negative 31. So let's go ahead and take a look at evaluating functions. You'll have to fill in some things that are missing on this page as well. It should say, given f of x equals 2x squared minus 8. We're going to find each value. So first they want us to find f of 6. All that means is we're going to be plugging in 6 for every x value that they gave us. So we're going to have 2 times 6 squared minus 8. We're going to do our 6 squared first. So we're going to have 2 times 36 minus 8. Remember, we always want to use PEMDAS. We want to follow our order of operations. So we're going to have 72 minus 8, which equals 64 for our final answer. For f of 2y, we're just going to plug in 2y for every single x we have. So now we can evaluate this. We're going to do our exponent first. So we're going to have 4y squared minus 8, which is going to be 8y squared minus 8. And that's going to be our answer. One mistake that I see a lot of students make, they don't want to leave a y in the final answer. But if they give you a variable to start off with, you're going to end up with the variable in your final answer. So that's okay. Down here on example B, it should say g of x equals 0.5x squared minus 5x plus 3.5. And first they want us to plug in 2.8. So we're going to have 0.5 times 2.8 squared minus 5 times 2.8 plus 3.5. And if we evaluate that, we're going to end up with negative 6.58 for our final answer. For g of 4a, we're plugging in 4a for every value of x. So we're going to have 0.5 4a squared minus 5 times 4a plus 3.5. And if we evaluate that, we're going to end up with 8a squared minus 20a plus 3.5 for our final answer. There's a few practice problems down at the bottom. You don't have to complete those, but I know that some of on your notes it's missing some information. So I went ahead and wrote the information here just in case you want to do those for extra practice. Your actual homework can be found under the assignments, and I believe it's on section 2-1 and 2-2. So now you can complete the part that's over 2.1, and you'll have to wait until you watch the next set of notes to be able to do the rest of those problems.